Observe the difference between these two results. On the left is a dense, heavy block of cooked dough. On the right, a perfectly airy, golden brown Ugandan bread loaf. This transformation from a heavy lump of flour into a light loaf depends on a single biological agent. That agent is yeast, a microscopic, single-celled living organism known as Saccharomyces cerevisiae. Because yeast is a living organism, it remains dormant until its environment provides three specific conditions: warmth, moisture, and sugar for food. Successful yeast cookery is the practice of managing these biological variables to control the final texture of the food. Temperature is the most critical variable. Since yeast is alive, the temperature of the water used during mixing determines whether the organism survives to do its work. These three states show the impact of temperature. Cold water keeps the yeast dormant. Boiling water kills the organism instantly. Only warm water triggers the yeast to wake up and begin multiplying. Testing the yeast in a small amount of warm water with a pinch of sugar ensures it is active before beginning the full recipe. Once active, the yeast begins to consume the sugars present in the flour or added to the mixture. This equation shows the chemical reaction. As yeast digests sugar, it produces carbon dioxide and ethanol through fermentation. However, without a structure to contain it, carbon dioxide bubbles simply escape, leaving the dough flat. To trap this gas, we knead the dough. Stretching forces two wheat proteins, gliadin and glutenin, to bond, forming an elastic network called gluten. This mesh catches the carbon dioxide. As gas increases, the gluten stretches, making the dough rise. Let's look at a common failure. In this image, the dough is being stretched, but it tears immediately. Pause the video for a moment. Identify what structure is missing here and the mechanical action required to fix it. The tearing indicates that the gluten network is not yet fully developed. The solution is more vigorous kneading, until the dough passes the windowpane test, stretching thin enough for light to pass through without breaking. A fluffy loaf is the direct result of balancing biological gas production with mechanical structural strength. These biological principles also apply to traditional Ugandan products like bushera, a fermented cereal drink where fermentation continues until it is consumed. The process begins by germinating the millet. This activates enzymes, represented by scissors, that break down starches into simple sugars. These feed wild yeast and lactic acid bacteria, producing organic acids that give bushera its signature tangy flavor. Whether the goal is the structure of a loaf or the flavor of a beverage, the core requirement of feeding and managing yeast remains the same. You can diagnose baking failures by tracing physical results back to their biological causes. This table identifies the most common issues: a lack of rising points to dead yeast or excessive heat, while a dense texture indicates insufficient kneading. Visualize the complete bread-making cycle. It starts with mixing, followed by kneading to establish gluten. Next is proving. In a warm place, yeast ferments, producing gas to double the volume. Finally, baking in a Chico oven expands gases before killing yeast, setting the structure. By respecting the environmental needs of this living organism, you can turn simple flour and water into complex, airy breads and traditional drinks. For more O-level science and home economics content, visit yaka.cc to explore our complete interactive curriculum.